Alright guys, so today in class we talked about bonding, and now I'm going to teach you how to use a certain notation to represent the bonding that occurs between different atoms. Now first of all, it's important to realize that bonding is going to take place using only the outermost electrons of an atom. Now the outermost electrons are what we call valence electrons. And these are the electrons that are going to participate in our bonds. Now first of all, let me teach you how to identify how many valence electrons an atom has, seeing as this will be important to you all in determining what sort of bonds are formed. So let's just take sodium for example. The electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. So what you do to find the valence electron is you look on the highest energy level, which in this case is 3, and then count the number of s and p electrons found within that energy level, which in this case is 1. So sodium would have 1 valence electron. If we consider magnesium, it would be 1s2, 2s2, 2p6, and 3s2. Okay. Again, we look at the highest energy level and count the number of s and p electrons. So this would have 2 valence electrons. Now, let's do one more example. Let's take, for example, phosphorus. Its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. So again, go to the highest energy level and just look for the s and p electrons, which in this case we have 2s and 3p. So that would be for a total of 5 valence electrons. Now you'll notice the number of valence electrons also corresponds to the group number of the element on the periodic table. For example, sodium has 1 valence electron and it's in group 1. So all things in group 1 have 1 valence electron. Magnesium is in group 2 and it has 2 valence electrons. So likewise, all elements within group 2 will have 2 valence electrons. Now, we see for our purposes we're going to kind of skip over the transition metals and just continue on with the main block elements. Now if you'll notice, sometimes on periodic tables you'll see this called 3A, 4A, 5A. And so what that's going to correspond to is the number of valence electrons for elements within this group. So elements in group 13 will have actually 3 valence electrons. So you can kind of just think about the 10 being taken off. Elements in group 4A or group 14 will have 4 valence electrons, so on and so forth, all the way over to the noble gases, which have 8 valence electrons. So it's going to be really important to be able to identify how many valence electrons an atom has. Now, when we want to keep track of the valence electrons of just a single atom, we're going to use what's called electron-dot notation. Let me see if I can adjust the lighting a little bit. I've got some shadows going on. Let's see if this is any better. Okay. So in electron-dot notation, what you're going to do is when you're given an element, you're going to write the symbol of the element, in this case calcium, and then you add a dot for each valence electron. So calcium, if we look on the periodic table, here it is in group 2, so it has 2 valence electrons. So I'm going to start and place one here and the other here. So that would be 2 valence electrons. If we had done potassium before it with just 1 valence electron, that would go there. Now as we keep working our way across this 4th period, I'll just go ahead and write out all the elements in the main blocks. We gradually continue to add valence electrons. There's 3. Here's 4. Now here we can pair up 5, 6, oops, there's 6, now here's 7, That's what 7 should look like. And then here's 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is electron dot notation. Again, that's simply the symbol of the element, and then you place dots around it to indicate the number of valence electrons. Okay? Now, however, we can also use a similar notation to represent molecules, which is where we have more than one atom bonded together. And that's going to be known as Lewis structures. Now there are 3 parts of a Lewis structure that are important to realize. One is the chemical symbol. Now this is on page 175. That's going to correspond with what I'm about to say. So the chemical symbol, in this case if we're dealing with carbon, is simply going to represent the nucleus and all of the inner shell electrons of the carbon atom. So this would represent the nucleus and the 1s2 electrons. Okay, so that's the symbol. Now, if you happen to see a dash between 2 symbols, that's going to represent a bond. Okay, and that bond is going to be 2 electrons, or what we know as an electron pair. So anytime you see a bond, you should really be thinking that that represents 2 electrons that are being shared between those atoms. Now sometimes you may also see things like this, which looks kind of similar to what we saw before. So, well, I'll do a different example, so we won't just use carbon. Let's say we have 2 fluorines. When you see dots attached to just one atom, that means that these are unshared electrons. So this line represents electrons that are shared between these 2 fluorines, but these dots are saying that these electrons, this electron pair, is not shared with the other fluorine, but is instead isolated on this fluorine. So again, those are the 3 parts, the symbol, the dash, and the dots. Now let's move on to talk about how to actually draw Lewis structures. So, what we're going to do is to learn it by using an example, iodomethane. Okay? So the way we're going to work these problems is by first writing down the elements that we have. Here we have carbon, hydrogen, and iodine. Now we need to take note of how many of each element that we have. We have 1 carbon, 3 hydrogens, and 1 iodine. Now, the way we're going to write Lewis structures is by using what's called the supply and demand method. So what we're first going to do is to figure out how many valence electrons each atom supplies. So our supply is from our valence electrons. So if we look on the periodic table, carbon, I'll pull that up for y'all. Carbon is in group 4, so it has 4 valence electrons. So it supplies 4, and since there's only 1 carbon, it's a total of 4 valence electrons. Now hydrogen, each hydrogen will supply 1 valence electron, but since there are 3 hydrogens, we'll multiply that 1 by 3 to equal 3. Now iodine, it's in the group 17, so it has 7 valence electrons. But again, there's just 1 iodine, so it will supply a total of 7 valence electrons. And if we add that up, that's a grand total of 14 valence electrons. Now, let's consider the demand part. The demand is how many electrons we need in order to satisfy something known as the octet rule. So the octet rule states that most atoms prefer to have an octet of valence electrons. Now an octet just means 8, and that's kind of like what we looked at earlier when doing our electron-dot diagram. So this would be an octet of electrons, just like you can have an octave, which is 8 notes in music, or an octopus with 8 legs. So an octet is 8 electrons. 8 valence electrons. So for most atoms, this is kind of the ideal, most stable state. However, there are a few exceptions that I do want you to be aware of. For hydrogen, it's satisfied with only 2 valence electrons. And also for boron, we'll see it's satisfied with only 6. So, in reality, the octet rule isn't a rule that applies every time. It's more of a suggestion, but we'll see that it works fairly well for most atoms. All right, so carbon would normally want an octet of 8 electrons. Now again, we multiply how much one carbon would want by the number of carbon atoms, which in this case is just 1. Now hydrogen, we've already said it's an exception, so normally each hydrogen would only demand or want 2 electrons in order to satisfy the octet rule. Okay, but in this case we have 3 hydrogens, so we'll multiply that by 3 to equal 6. Now, let's look at this. So iodine, again, follows the normal octet rule and would want 8 electrons. There's only 1, so that would be 8. So if we total this up, 8 plus 6 plus 8, that's going to leave us with a demand of 22 electrons. Now, we need to figure out how many electrons we're going to have to share within a bond. So the way we do that is we take the electrons in demand and subtract the electrons that we already have supplied. All right, the difference between these two is 8 electrons. So this means this is the number of electrons that we're going to have to share. Now we've already talked about that electrons are shared in pairs within a bond. So if we divide by 2, that's going to tell us the number of bonds that we have to make. Now, a couple of key suggestions that will help you as you set up your Lewis structures. One, whenever you're working with carbon, it normally goes in the center. Otherwise, our typical rule is that the least electronegative atom is placed in the center. But here we have carbon, so we'll go from there. All right, so we know that we have to form 4 bonds. So I'm going to start out by symmetrically placing those bonds around carbon. And then I'll fill in my other elements. Hydrogen, 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 and iodine. Now, a couple of things that are important to note about hydrogen and the halogens. So hydrogen can only form 1 bond. And then likewise, most halogens, for our purposes, will only be able to form 1 bond as well. All right, so we've used up our 4 bonds, and we know that hydrogen and our halogens cannot form any other bonds. So now, let's go ahead and fill in the remainder of our electrons. So now that we've placed our bonds, we need to see who else is lacking an octet. So hydrogen, we know its kind of false octet is just 2. So here are 2 electrons that correspond to hydrogen, so it's satisfied. These 2 electrons are also shared by hydrogen, so it's satisfied. These 2 are shared by hydrogen, it's satisfied. Okay, so now let's check on carbon. So carbon already has 2, 4, 6, 8, so there's its octet. Okay, so we've already used 8 electrons, and we know that we had 14 total. So that means there's 6 remaining that we need to place. And those 6 we'll use to complete the octet of iodine. So we'll place those. 1, 2, 3, 4, 5, 6. All right. So now everything is satisfied with an octet. Iodine has 2, 4, 6, 8 electrons. So this would be our complete Lewis structure for iodomethane. All right, continue on to part 2 to see another example.